Do you believe that 124 light-years from Earth, there exists a planet called K218b? One that has captured attention through the first signals that begin to shake the way humanity searches for life in the universe. Orbiting a red dwarf star, K218, smaller and cooler than our Sun, at a distance just right to keep water on its surface from freezing solid or evaporating completely. But with a mass 8.6 times that of Earth, this is a super-Earth filled with paradoxes, a world where crushing pressure could destroy any familiar biological structure. With gravity about 30% stronger than Earth's, any life that exists here would have to endure extreme physical stress. Yet it is precisely this alien environment that opens an entirely different scenario from everything we have known about the possibility of life beyond Earth. Join us as we step into a deeper journey to uncover the mysteries of K218b and discover why this world is reshaping the way we define life. When modern space telescopes turned their gaze toward K218b, the shock did not come from seeing alien life, but from being forced to rethink how life itself can be observed. Through transmission spectroscopy, scientists confirmed the presence of carbon dioxide and methane in the planet's atmosphere, along with signals consistent with water vapor. This is not vague speculation, but peer-reviewed science results published in respected journals based on independent observations and detailed atmospheric modeling. K218b has a radius roughly 2.6 times that of Earth, an estimated mass 8 to 9 times greater, and orbits the red dwarf star K218b at a distance that allows surface or lower atmospheric temperatures to remain within the range where liquid water could exist. Its host star shines with only a few percent of the Sun's brightness. Yet because the planet orbits so closely, its year lasts just about 33 days. What truly matters is how science interprets these gases. On Earth, methane is often associated with biology anaerobic microbes, the digestive systems of animals, and oxygen-poor ecosystems all release methane. Yet methane is not exclusive to life. Carbon dioxide, likewise, is both a product of biological respiration and a common component of the atmospheres of lifeless worlds such as Venus or Mars. Water vapor signals the presence of water, but says nothing about whether that water participates in biology. What K218b's data actually reveal is an active atmosphere. It is not chemically simple, static, or easily predictable. The coexistence of methane and carbon dioxide under specific temperature conditions suggests a system that is continuously replenished or actively rebalanced. On Earth, such an atmosphere would be difficult to maintain for long, without ongoing biological processes disrupting thermodynamic equilibrium. Even the most extreme microorganisms on Earth, organisms that tolerate high radiation or extreme cold, would struggle to survive for long if directly exposed on Europa's surface. Yet high-resolution images reveal that its surface is almost entirely lacking large impact craters, an unusual feature for an icy body that has more than 124 light-years away. With enough precision to seriously discuss extraterrestrial biology, shows that the surface is not always the most important place. Sometimes, conditions so hostile as to be unacceptable are themselves a sign that the answers lie elsewhere. In Europa's case, all scientific evidence leads to the same stark and clear conclusion: if life exists, it must be hidden from the surface. It is from this point that the exploration must turn in a new direction, one where long-held assumptions about life itself are finally put to the test. When we look back at Earth's biological history, the assumption that life requires oxygen and sunlight begins to unravel. For nearly the first 2 billion years, Earth had almost no free oxygen in its atmosphere. Oxygen levels were millions of times lower than they are today. Yet life not only existed, it flourished. Anaerobic microorganisms dominated the planet for a span of time far longer than the entire history of humanity combined. Oxygen, which we now consider a fundamental requirement for life, was once a biological toxin that triggered one of the greatest extinction crises of the ancient world during the Great Oxidation Event around 2.4 billion years ago. If oxygen were used as the defining criterion in the search for life, most of Earth's own biological history would be overlooked. At the bottom of the oceans, where sunlight disappears after just a few hundred meters, fully developed ecosystems thrive at depths of 2,500 to more than 4,000 meters. Pressures here can exceed 400 bar. Temperatures hover near freezing. Yet beside hydrothermal vents, water can surpass 350 degrees Celsius without boiling due to the immense pressure. In this seemingly contradictory environment, life does not depend on photosynthesis. The foundation of the entire ecosystem is formed by chemosynthetic bacteria and archaea, drawing energy from reactions involving hydrogen sulfide, methane, hydrogen, and hot minerals rising from Earth's mantle. Fish, giant tube worms, mollusks, and many other complex organisms occupy only the upper layers of a living network that functions entirely without light. Sunlight, then, is not a mandatory condition. What truly matters is a stable energy source and the ability to sustain chemical reactions over long periods of time. On Earth, geochemical evidence suggests that life may have emerged just 300 to 500 million years after the planet cooled enough for liquid water to exist. K218b orbits a red dwarf star, a class of stars that makes up roughly 70% of all stars in the Milky Way. Red dwarf light is dimmer than the sun's, rich in infrared radiation, and often accompanied by stellar flares. During early stages of stellar evolution, for years, these traits were considered hostile to life. But if life does not require intense light for photosynthesis, if it can exist beneath the surface or within deep oceans, then red dwarf stars are no longer adversaries. Instead, they may represent stable energy sources lasting tens to hundreds of billions of years, far longer than the sun's lifespan. If life emerges rapidly once conditions allow, as Earth's history suggests, then in a universe containing hundreds of billions of galaxies, each with hundreds of billions of planets, the implications are profound. Modern biology cannot yet provide a definitive answer, but studies of extremophiles from bacteria thriving in acidic lakes to organisms capable of withstanding ionizing radiation thousands of times stronger than what would kill humans demonstrate that life is not optimized for comfort but for survival. As scientists begin to accept the possibility that life can exist in environments utterly unlike our own, a new hypothesis takes shape. If a planet does not require an Earth-like surface, if it can be covered by a global ocean and wrapped in a hydrogen-rich atmosphere, then traditional biological limits are pushed far outward. From the question of life unlike us, scientific thinking is forced into a new landscape, one where deep ocean worlds, high pressures, and faint light become serious candidates for life. It is at this intersection that the Hycean world hypothesis emerges, opening the next chapter of the story, a type of planet where, if life exists, it would be entirely unlike anything Earth has ever known. As familiar criteria for Earth-like planets gradually reveal their limits, science is forced to expand its mental map. Not to search for a second Earth, but to accept a deeper truth. The universe has no obligation to replicate our environment. It is within this context that the Hycean world hypothesis emerged not as a declaration, but as a serious theoretical framework grounded in physics, chemistry, and verified exoplanet data. A Hycean world describes planets covered by global oceans and wrapped in thick, hydrogen-rich atmospheres, often orbiting red dwarf stars. In fact, planets with sizes between Earth and Neptune roughly 1.5 to 3 times Earth's radius and 5 to 10 times its mass are the most common type of planet in the galaxy. What is striking is that our own solar system contains no representative of this class. Hycean worlds may therefore represent a planetary norm that humanity has never experienced. According to atmospheric and planetary structure models, a Hycean world can retain light hydrogen thanks to sufficiently strong gravity, while still maintaining liquid water in the form of a deep ocean tens to hundreds of kilometers thick. A hydrogen-rich atmosphere creates an efficient greenhouse effect, stabilizing ocean temperatures at warm levels, even when the planet receives less energy from its star than Earth does. In many scenarios, surface ocean temperatures are estimated to fall within a range of 0 to 100 degrees Celsius, suitable for complex chemistry to persist over long timescales. Light from red dwarf stars, the primary energy source for these worlds, is weaker than sunlight and concentrated largely in the infrared. This may leave the upper ocean relatively dark, but it also reduces temperature fluctuations and dramatically extends stellar lifespans. Red dwarf stars can exist for trillions of years, far exceeding the Sun's expected lifetime. This opens a startling possibility. High-Cean worlds could sustain stable environments for prebiotic and biological chemistry far longer than any Earth-like planet. In such a setting, if life were to form, it would face little pressure to evolve rapidly or adapt to violent climate swings. It could evolve slowly, extremely slowly, within an environment that remains nearly unchanged for billions of years. And it is precisely this stability, not comfort, that may be the key ingredient for life. If life exists on a High-Cean world, scientific models suggest it would most likely inhabit deep ocean layers rather than the surface regions where radiation from the host star is almost completely eliminated, pressure is high but stable, and temperature variation is minimal. Energy would not come from light, but from chemical reactions involving hydrogen, methane, ammonia, and minerals within the planet's mantle. These reactions could drive slow but continuous energy cycles, sufficient to sustain self-organizing chemical systems. At this level, life, if present, might exist only in microscopic forms, leaving no clear atmospheric signature. On a High-Cean world with no continents, no fire, and no exposed metals, any intelligence that emerged would be forced down entirely different evolutionary paths. Rather than vision based on strong light, intelligent organisms might develop extraordinarily complex acoustic communication, similar to but far surpassing that of whales and dolphins on Earth. Sound travels more efficiently in water than in air, especially at low frequencies, enabling communication across vast distances. An ocean-based intelligence might hear its world in ways humans can scarcely imagine. Another possibility involves bioluminescence, a phenomenon already widespread in Earth's oceans. In a dark environment, networks of luminous organisms could encode information through rhythm, color, and intensity. On large scales, vast underwater light maps could function in ways analogous to written language or visual signaling in human societies. A more speculative, highly theoretical possibility is that intelligent life could exploit planetary magnetic or electric fields. Many Earth organisms already sense magnetic fields for navigation. On a Hycean world, where ocean currents and planetary structure might generate stable electromagnetic fields, intelligence could evolve to use and modulate these fields for communication or interaction with the environment. If such intelligence existed, the concept of technology would be entirely different. There would be no fire for metallurgy, no wheels for land-based infrastructure. Any structures might instead consist of pressure, adapted frameworks, vast biological scaffolds anchored in the deep ocean, or luminous networks stretching hundreds of kilometers existing not as cities, but as something closer to a collective nervous system. These ideas are strongly influenced by science fiction, and it must be stated clearly, there is currently no scientific evidence to support them. To date, no data indicate that intelligent life exists on K218b or on any Hycean world. The Hycean hypothesis, therefore, is not merely a theory about planets. It is a test of how humanity understands itself. And if life elsewhere exists, in forms that never produce signals we know how to recognize, then is the silence of the universe truly evidence of loneliness? The Hycean hypothesis forces science to confront its own limits. We cannot send probes, drill into alien oceans, or meet any form of life. All we have is light and faint chemical traces. If life exists there, whether microscopic or intelligent, how would we recognize it from hundreds of light years away? If life truly exists on K218b, more than 124 light-years away, every familiar notion of exploration collapses. There would be no probes, no landing robots, no samples returned to laboratories. If life exists there, it will not be discovered through direct contact. It can only be inferred through light, mathematics, and universal physical laws. When K218b passes in front of its host star, a small fraction of starlight is absorbed by the planet's atmosphere. Each molecule absorbs light at specific wavelengths, creating dark lines in the observed spectrum. By analyzing these lines, scientists can determine the chemical composition of the atmosphere, a technique known as transmission spectroscopy. This method is not new, but for the first time in history, The sensitivity of current generation telescopes has pushed it to a level where serious discussion of extraterrestrial biology is possible. However, in a closed system without a continuous energy source, chemical reactions tend toward equilibrium, a state in which significant change ceases. When this principle is applied to exoplanets, science must proceed with far greater caution. Geochemical processes, volcanic activity, radiation from the host star, or even asteroid impacts can also produce unusual atmospheric configurations. K218b places us at the threshold of a new scientific era, one in which knowledge is no longer built from direct observation, but from extraordinarily subtle indirect traces. It forces biology to expand its definition of life, philosophy to reconsider humanity's place, and society to confront a foundational truth. Earth is no longer the sole reference point for life in the universe. The greatest shock will not come from technology, but from meaning itself, from what scientific data may ultimately reveal about our existence. From a scientific perspective, confirming life beyond Earth, even in the form of simple microorganisms, would be the greatest revolution in biology since Darwin published the theory of evolution. For the first time, biology would no longer be the science of a single planet. Life would no longer be studied as a phenomenon tied exclusively to Earth's unique geological history, but as a process that can arise under different physical conditions. This would force biology to expand its definition of life, moving beyond DNA, liquid water, and familiar chemistry toward more universal principles. The ability to sustain itself, exchange energy, and evolve over time. Astronomy and planetary science would be transformed just as fundamentally. For decades, exoplanets have been classified mainly by mass, radius, and orbital parameters. If life were confirmed on a world like K218b, those criteria would no longer be sufficient. Planets would be evaluated not by how closely they resemble Earth, but by their ability to maintain stable biochemical systems over long timescales. Yet the deepest impact would likely occur not in laboratories, but in human consciousness. If life were confirmed in another star system, a long-held belief would collapse. Earth would no longer be seen as the only oasis, but as one example within a far larger set. The existence of bacteria, or simple organisms on K218b, would say nothing about civilizations, consciousness, or technology. But that is precisely what makes the shock more profound. It reveals that life does not need to rise to intelligence to possess cosmic significance. If life is not exclusive to Earth, then protecting life, including life on our own planet, takes on a broader meaning. It raises questions about humanity's responsibility toward the world we inhabit and toward exploring other worlds without destroying ecosystems we do not yet understand. When generated from below, it drives thermal convection within the ocean. Warmer, less dense water rises, while colder, denser water sinks, establishing slow but continuous circulation. This turns Europa's ocean into a dynamic system where material is mixed. Energy is distributed, and chemical reactions have repeated opportunities to occur. In the science of life, such circulation is essential. A completely stagnant environment eventually reaches chemical equilibrium and becomes dead. A convective environment, by contrast, maintains imbalance, and it is precisely this imbalance that underlies all biological processes. Even more importantly, structural models of Europa suggest that the ocean may be in direct contact with the underlying silicate rock layer. On Earth, the locations where primitive life is thought to have emerged earliest were not at the surface, but on the ocean floor, where hot water reacts with the discovery of life on K218b would not be merely an astronomical finding. It would be a historic turning point, shaking the deepest pillars of human understanding. A planet covered by vast oceans and wrapped in a complex atmosphere of water vapor, methane, and carbon dioxide sends a powerful message. The conditions that give rise to life are not a privilege unique to Earth. These chemical signatures represent the first empirical hints that the universe is not silent or lifeless as we once imagined, but may be alive with processes unfolding in forms humanity has never conceived. Yet K218b is also a lesson in humility and scientific discipline. It reminds us that the path to understanding the universe must be built on verified evidence and precise measurement, not on assumptions shaped by human expectation. If the hypotheses surrounding K218b are confirmed, the very concept of life will have to be rewritten. Earth would no longer stand as a solitary oasis in a vast cosmic darkness, but as part of a far larger and more intricate web of existence. We would be forced to accept a new reality, that on distant worlds, utterly different in structure, pressure, and environment, life can still emerge and evolve in silence. Such a discovery would not only bring an end to the era of cosmic solitude, but also open a new chapter in humanity's journey, a chapter in which we begin to learn how to understand, and perhaps one day communicate with, a universe filled with unnamed neighbors. What would happen if we left Earth, traveled beyond 40 light years, and reached a distant, unfamiliar world called Gliese 12b, a planet nearly comparable in size to Earth, a place where light does not appear in familiar colors, yet gravity, surface conditions, and geological processes lead scientists to believe it could sustain a stable environment. But that is not all. If the journey continues, moving even farther, 48 light years from the Sun, you arrive at Gliese 1214b, a world believed to be an ocean planet where pressure and temperature are thought to allow the existence of unfamiliar and previously unseen forms of life. With these discoveries, we are standing at the edge of entirely new physical concepts surrounding what we call ocean planets. Let us continue exploring what we have never known about these mysterious worlds. When humanity decides to leave Earth and journey to Gliese 12b, a voyage spanning tens of light years, what would actually be waiting ahead? As the spacecraft enters the Gliese 12 system, the first thing you would notice is the light, with the central star being a red dwarf, smaller and cooler than the Sun. Its light is not the familiar white-yellow glow we know, but instead bathes space in a deep, elongated red hue, soft, persistent, and inescapable. Red dwarfs emit less energy, yet they remain stable for tens of billions of years, far longer than the Sun's expected lifespan. Observations indicate that Gliese 12b's radius is only slightly larger than Earth's. Estimates of its mass suggest that surface gravity would not differ dramatically from what we experience at home. If you stood on Gliese 12b, your body would not be crushed, as it would be on a super-Earth, nor would you feel nearly weightless like on Mars. The gravity here would feel familiar enough for humans to walk, stand, and function for extended periods, at least from a mechanical perspective. Under the constant red light of its host star, the sky would likely appear dark orange or reddish-brown. The ground would reflect light in unfamiliar ways, and if vegetation existed, it would not be green like plants on Earth. Models of photosynthesis suggest that under red dwarf light, living organisms could evolve much darker pigments, deep red, purple, or even nearly black, in order to absorb energy more efficiently. Does Gliese 12b have a solid surface? Its estimated density strongly suggests that it is most likely a rocky planet, or at least a world dominated by a rocky interior. This opens the possibility of continents, mountains, and geological processes similar to those on Earth. And although there is no direct evidence yet of oceans or rivers on Gliese 12b, its position within the zone where liquid water could exist makes this hypothesis plausible. If water is present on the surface, it might take the form of shallow seas, large lakes, or even limited oceans interspersed with rocky land masses. Gliese 12b may be a world balanced delicately at the threshold between dryness and inundation. In addition, many planets orbiting red dwarfs tend to become tidally locked, with one side permanently facing the star, while the other remains in eternal darkness. If Gliese 12b is in such a state, it would have a hot day side and a cold night side, with a narrow twilight zone along the terminator where conditions could be the most moderate. This region might be the only place where humans could exist for long periods, if they could exist at all. To truly understand what that means, we are forced to look toward another nearby and equally strange world on the list of known exoplanets, Gliese 1214b, where the journey is no longer about where humans might stand, but about worlds that exist entirely beyond our ability to physically reach or endure. When scientists calculated the average density of Gliese 1214b, the result came out far lower than that of Earth. This means the planet cannot be composed solely of rock and metal. Lighter components must make up a large fraction, and the most plausible candidate is water. Not water in the familiar form of rivers and lakes, but an immense volume of water that could account for tens of % of the planet's total mass. Stronger gravity helps the planet avoid losing water and gases to space, even under radiation from its red dwarf star. Spectroscopic observations indicate that Gliese 1214b possesses a thick, opaque atmosphere that may contain water vapor, hydrogen, and other complex molecules, strongly suggesting an ocean planet where water covers nearly the entire surface. Compared with Gliese 12b, The difference lies not in distance from the star or the amount of light received, but in mass. An increase of just a few times Earth's mass is enough to push a planet into a global ocean state. When water becomes abundant enough to blanket the entire surface, familiar geological processes, weathering, and the carbon silicate cycle are disrupted, and the rocky core becomes isolated beneath a thick water layer, no longer interacting directly with the atmosphere. On Earth, complex life evolved thanks to a delicate chain of balances. Volcanoes release gases. Rain draws carbon down into rocks. Plate tectonics recycles material. And oceans act as a thermal buffer. On an ocean planet, like Gliese 1214b, that chain is broken. There are no continents to weather, no plate tectonics operating as we know them. And the atmosphere may evolve along entirely different pathways. Ironically, the very factors that make Gliese 1214b so alien to humans may allow it to remain stable for extremely long periods. A thick atmosphere helps distribute energy and shield the surface from radiation. Water, once it surpasses a certain threshold, is no longer merely a support for Earth-like life, but becomes the defining environment of an entirely different biosphere. An ocean hundreds of kilometers deep is not just a surface feature, but a vast three-dimensional space where light energy can scarcely penetrate to the depths. The transition from Gliese 12b to Gliese 1214b therefore carries significance far beyond these two specific planets. In oceans like these, life, if it exists, is no longer governed by sunlight in the way we understand it, but must instead follow entirely different physical and biological laws. Where oceans may be dozens of times deeper than those on Earth, pressure in the lower layers becomes so extreme that water no longer behaves like an ordinary liquid. Under those conditions, water molecules rearrange into exotic ice phases that exist alongside high temperatures. A state that on Earth can only be created in laboratories. Extreme pressure would force life, if it emerges, to abandon all rigid structures. Bones, shells, and supporting frameworks as we know them would become fatal weaknesses. Organisms in this environment, according to scientific reasoning, would most likely have soft, flexible structures with almost no internal cavities. On Earth, creatures living in the deepest ocean zones, such as the Mariana snailfish, have given us an early clue: soft, gelatinous bodies, few gas-filled spaces, and slow but efficient movement. Even on Earth, sunlight penetrates only about 200 meters before disappearing completely. Below that depth, the ocean exists in permanent darkness, meaning that much of the biosphere, if it exists, would develop without relying on photosynthesis. When light disappears, energy comes from chemistry, with reactions involving hydrogen, methane, sulfur, and other reducing compounds becoming the primary energy source. Life turns downward toward places where energy is generated by geochemical interactions. And in such environments, organisms do not need eyes in the familiar sense, as vision becomes useless without light. Instead, other senses are prioritized. Detecting pressure, vibrations, chemicals, and currents. Communication, if it exists, may occur through chemical signals or pressure waves traveling through water. In a deep and quiet ocean, even a small change in pressure can travel great distances, a form of hearing that humans can scarcely imagine. One of the most striking biological possibilities is bioluminescence. On Earth, many deep-sea organisms produce their own light to attract prey, communicate, or confuse predators. On an ocean world where starlight is nearly absent, bioluminescence could become the language of light, of life. These glowing organisms would not illuminate their surroundings, but instead generate signals essential for survival. Another possibility is the existence of free-floating organisms that are not anchored to the seafloor or the surface. Life here would not need to swim in the traditional sense. Organisms could adjust their body density to remain suspended at desired depths, drifting with the slow currents of a planetary ocean. life becomes a three-dimensional phenomenon, no longer confined to a surface plane, as it is on Earth. Gliese 1214b thus becomes a natural laboratory for these ideas. If that planet truly has a global ocean, a thick atmosphere, and a stable source of chemical energy, then the existence of life, though unreachable, is entirely reasonable under the laws of physics and chemistry. Life there would not require continents, a familiar day-night cycle, or an oxygen-rich atmosphere. It would need only energy, a solvent, and time. Three elements that ocean planets can provide in abundance. If life can thrive in environments where humans can never set foot, what does that say about our place in the universe? Could it be that most life in the universe exists in places we will never physically reach, directly observe, or even fully understand? Ocean worlds force us to confront a fundamental truth. Life can arise wherever the laws of physics allow, and it evolves along paths we do not control. In oceans beyond Earth, life may be abundant and diverse. The difference is not merely environmental, but biological destiny. And when Gliese 12b and Gliese 1214b are placed side by side, what stands out is not their distance or the light of their host star, but how two worlds arrive at completely different biological outcomes from differences that appear very small. They share similar beginnings, both formed around red dwarf stars. Both lie within regions where liquid water could exist. And both are not far from Earth by cosmic standards. Gliese 12b represents a state of just enough where water exists but does not dominate. The rocky core still interacts with the surface. Geology can remain active, and the planet preserves a familiar layering of rock, water, and atmosphere. This stratification enables long-term cycles, such as carbon cycles, thermal cycles, and possibly even early biological cycles. If life were to arise on Gliese 12b, it would not need to be complex. It could exist in microscopic, localized forms, adapting to stable local environments, similar to early life on Earth billions of years ago. By contrast, on Gliese 1214b, water is no longer a supporting factor but an overwhelming one. A global ocean isolates the rocky core. Severing many geochemical mechanisms that Earth relies on to maintain climate balance. In this scenario, life, if it exists, does not develop on the stability of solid ground, but on the stability of an immense body of water. Instead of rooting, building, and expanding across land, the biosphere of Gliese 1214b would distribute itself by depth, spreading through the three-dimensional space of the ocean. On Gliese 12b, volcanoes release gases. Rain and oceans absorb them, and chemical reactions regulate atmospheric composition over time. This dialogue creates a slowly changing environment, stable enough for life to adapt, yet flexible enough to allow evolution. On Gliese 1214b, that dialogue is nearly silent. The rocky core is locked beneath immense water pressure, and the planetary surface becomes a closed system where water and atmosphere interact more with each other than with rock. The biological consequences of these two scenarios are very different. And on Gliese 12b, life, if it emerges, may face many challenges, but also many evolutionary opportunities. A solid surface allows diverse microenvironments to form, such as rock crevices, shorelines, and semi-submerged zones. Each microenvironment becomes an evolutionary laboratory where organisms test different survival strategies. Gliese 12b is not safe or perfectly stable, yet it remains within a realm where humans can imagine access, study, and even a distant landing in the far future. Gliese 1214b does not. It marks a threshold beyond which the concept of access loses meaning. not because life is absent, but because the environment that sustains life no longer has room for us. Two planets, two biological destinies, and two ways the universe answers the same question: how can life exist? One answer suggests life can be slow, fragile, and dependent on subtle balance. The other suggests life can be abundant, powerful, yet utterly alien and unreachable. And it is here that our line of thought begins to shift. As we realize that most water-rich worlds in the universe may follow the Gliese 1214b scenario, and a truth emerges. Many oceans out there may teem with life, yet not belong to us. Life continues, evolves, and transforms entirely independent of whether humans can ever set foot there. And some oceans, though full of life, will remain forever beyond human survival. From a cosmic statistical perspective, ocean planets may be far more common than Earth-like worlds. From a physical standpoint, ocean planets are not anomalies. They may be the universe's default, while Earth is the rare exception. But what is typical for the universe does not equate to human habitability. For humans, a planet is only truly habitable when there is ground to stand on, to build upon, and to shape into a living space. Land is not just a physical foundation. It is also a psychological and biological one. The human body evolved to tolerate low pressure, moderate gravity, and direct contact with solid surfaces. On an ocean planet, these conditions do not exist. There are no shorelines to step onto, no highlands for refuge, and no place to build a long-term artificial ecosystem. Even if technology allowed humans to exist temporarily, within floating stations, massive submersibles, or sealed environments, that existence would still be borrowed. Humanity cannot expand, cannot settle, and cannot build a sustainable civilization in an ocean hundreds of kilometers deep. Every artificial structure would constantly battle pressure, corrosion, and complete isolation. On a planetary scale, this is not a solution, but an unwinnable struggle. What matters is that this inaccessibility does not negate the possibility of life. On the contrary, scientific analysis suggests that ocean planets may be remarkably stable over long timescales. Deep oceans act as enormous thermal buffers. Thick atmospheres help distribute energy, and chemical energy sources from within the planet can sustain a biosphere for billions of years. Life there does not require surface light, continents, or the presence of humans to thrive. And it is precisely this separation that creates the greatest paradox in the search for extraterrestrial life. We may detect signs of life through atmospheric composition, chemical signals, or biological anomalies, yet never be able to reach it directly. Ocean planets are therefore not a failure of interstellar ambition, but a test of intellectual maturity. Can humanity accept that the universe is larger than its needs? And once we accept that, a subtle shift occurs in how we see Earth itself. A planet with just enough water, with continents, active geological cycles, and a stable atmosphere, conditions once taken for granted, suddenly appears extraordinarily fragile and precious. In this context, Gliese 12b is no longer a target for conquest, but a mirror reflecting the rare balance Earth possesses. The oceans out there may be teeming with life, but they are not waiting for us. They exist as a parallel branch of evolution, a reminder that life does not require humanity to have meaning. And from that realization, this journey must end with a final question. Not about planets, but about ourselves. If the universe was not designed for humans, how should we understand our place within it? Setting foot on Gliese 12b or Gliese 1214b is not merely a journey of space exploration, but a turning point that redefines humanity's position in relation to planetary bodies beyond the solar system. These worlds do not possess the stillness of lifeless rocks, but instead are dynamic and suffocatingly extreme environments where water and pressure hold absolute dominance. Here, thick, water vapor-rich atmospheres envelop oceans hundreds of kilometers deep, generating immense pressure capable of distorting the familiar laws of thermodynamics. Beneath these vast oceans, in regions untouched by light, exist exotic states of matter such as high-pressure ice. Extraordinary physical structures that act as regulators of heat and energy, forming a planetary system entirely different from Earth's geological model. The existence of Gliese 12b and Gliese 1214b poses a profound challenge to our understanding of the nature of life in the universe. If any organisms are able to emerge and persist in these environments, they certainly would not rely on photosynthesis or the biological cycles we are familiar with. Instead, their survival would depend on extraordinary adaptations to eternal darkness, extreme pressure, and chemical energy sources originating from the planetary interior. This forces the scientific community to abandon outdated boundaries and expand the definition of a habitable zone, showing that life does not necessarily require blue skies or solid ground to take root. Ultimately, these enigmatic planets convey a profound message about the limitless diversity of evolutionary pathways in the universe. They demonstrate that the search for distant worlds is not merely about finding a comforting second Earth, but about confronting the vastness and strangeness of nature itself. Gliese 12b and Gliese 1214b stand as the clearest examples that we face an immense universe where every alien ocean conceals physical and biological mysteries far beyond human imagination and long-held assumptions. What if, within the intense radiation environment surrounding Jupiter, there existed an icy world that might still harbor life? That world is Europa, Jupiter's fourth largest moon. Smaller than Earth, yet concealing a secret that could change the course of scientific history. Using the highest resolution images ever obtained from Galileo, the Hubble Space Telescope, and recent close flybys by Juno, scientists have revealed a shattered icy landscape, so-called chaos terrain. Not the quiet, static impact craters seen on our own moon. Instead, Europa's surface is crisscrossed by a dense network of massive fractures and dark reddish streaks stretching thousands of kilometers across the ice. Even more striking, Hubble has detected towering plumes of water vapor rising hundreds of kilometers above the surface, suggesting that the ocean beneath the ice may be directly interacting with space. This could provide an ideal environment for life, similar to ecosystems found around hydrothermal vents on the ocean floor here on Earth. If we were to find life on Europa, then what would happen? Europa orbits Jupiter at a distance of only about 670,900 kilometers, and this very position places it at the heart of an invisible engine of destruction, the Jovian radiation belts. Jupiter possesses the strongest magnetic field of any planet, roughly 20,000 times stronger than Earth's. And this magnetic field traps high-energy charged particles, electrons, and ions, creating an extremely intense radiation environment. Europa lies deep within this region. Measurements from the Galileo mission and subsequent observations show that the dose of ionizing radiation on Europa's surface can reach approximately 5 sieverts per day. The average surface temperature is estimated to be around -160 degrees Celsius, and in dark regions or during extended nights, temperatures can drop to nearly -220 degrees Celsius. At these temperatures, water freezes hard as rock. Chemical reactions slow to the point of nearly stopping. And every familiar biological mechanism we know becomes unable to function. It is a world where heat is almost absent. Europa's atmosphere, if it can be called that, exists only as an extremely thin layer. Observations indicate that it is composed mainly of molecular oxygen, produced not by biology, but by a process known as radiolysis. High-energy radiation from Jupiter bombards the surface ice, splitting water molecules into hydrogen and oxygen. The lightweight hydrogen escapes into space, while the heavier oxygen remains trapped in a tenuous gaseous layer. The surface pressure of this atmosphere is trillions of times lower than Earth's atmospheric pressure. It is essentially a vacuum. Oxygen is present, but not to breathe, not to protect, and not enough to support any kind of ecosystem. Europa's surface thus becomes a realm with no stable liquid water, no climate cycle, and no natural shield against cosmic radiation. Even the most extreme microorganisms on Earth, organisms that tolerate high radiation or extreme cold, would struggle to survive for long if directly exposed on Europa's surface. Yet high-resolution images reveal that its surface is almost entirely lacking large impact craters, an unusual feature for an icy body that has existed for billions of years. This suggests that the surface is young and continuously being renewed. It shows that the surface is not always the most important place. Sometimes, conditions so hostile as to be unacceptable are themselves a sign that the answers lie elsewhere. In Europa's case, all scientific evidence leads to the same stark and clear conclusion. If life exists, it must be hidden from the surface. That question opens a door to a realm beyond direct imagery, but one where scientific data is becoming increasingly clear. A global subsurface ocean, dark, deep, and possibly the only place on Europa where life has a chance to exist. During the Galileo mission in the 1990s, magnetic field measurements taken as the spacecraft flew past Europa revealed an anomaly. Jupiter's magnetic field was distorted in a way that could only occur if a layer of electrically conductive material existed inside Europa. After ruling out other possibilities, scientists arrived at the most reasonable conclusion: a layer of liquid salty water rich enough in ions to induce electrical currents when interacting with Jupiter's immense magnetic field. Most current studies now converge on a relatively consistent scenario. Europa's outer ice shell has an average thickness of about 15 to 25 kilometers, beneath which lies a salty ocean reaching depths of roughly 100 kilometers, and deeper still may be a layer of silicate rock in direct contact with the water. This structure is critically important because it allows water and rock to interact, a key condition in many hypotheses about the origin of life. The scale of Europa's ocean far exceeds intuitive imagination. With Europa's radius of about 1,560 kilometers, a global ocean tens to hundreds of kilometers thick implies an immense volume of water. Estimates suggest that the total amount of liquid water on Europa may exceed all the water in Earth's oceans combined. Earth, despite being called the blue planet, actually has only a very thin layer of water covering its rocky surface. Europa is the opposite. Water may be the dominant component by volume, with ice serving only as a sealed outer shell. Europa's surface is almost entirely devoid of large impact craters, indicating that it is geologically young. Stretched, fractured, and overlapping ice bands reveal that the ice shell is not a rigid, immobile block, but a system capable of movement, cracking, and refreezing. These features are difficult to explain if what lies beneath is nothing more than solid ice, extending tens of kilometers downward. By contrast, they are consistent with an ice shell floating atop liquid water, able to bend, slide, and restructure over time. Salts detected on Europa's surface, including sodium and magnesium compounds, are thought to originate from the ocean below, transported upward through icy geological processes. This suggests that Europa's ocean is not completely isolated. It is an open system to some degree, open enough for chemistry to occur, open enough for essential components to be redistributed over long geological timescales. That thick, cold ice shell may also shield the ocean beneath from Jupiter's intense ionizing radiation. If the surface is a place where biology cannot survive, then, beneath the ice, the ocean may be a far more stable environment. One where complex molecules have time to persist, interact, and evolve. The existence of a global subsurface ocean on Europa forces us to reconsider Earth itself from a different perspective. On our planet, sunlight plays a central role in all major ecosystems. But if liquid water can exist stably for billions of years, if chemistry is sufficiently rich, then life, even in simple forms, may not require a sky, may not require day and night, and may not require photosynthesis. However, water and time alone are still not enough. A vast ocean, if completely still and cold, would ultimately become a chemical graveyard. To remain liquid, to drive chemical reactions, energy is required. The turning point came from observations by the Hubble Space Telescope. In observing campaigns that began in 2012 and were analyzed in greater depth in the years that followed, scientists detected unusual structures rising above the limb of Europa. They were not reflected light, not optical noise, but elongated columns of material extending roughly 100–200 kilometers above the surface. Spectral data showed that their primary component was water vapor. In the near vacuum environment around Europa, water disperses rapidly, yet its signature was distinct enough to be distinguished from any other phenomenon. What makes this discovery significant is not only the existence of the plumes, but their intermittent nature. They do not appear continuously like steady jets, but are observed only at certain times, often coinciding with specific positions of Europa along its orbit around Jupiter. This suggests that the plumes may be directly linked to tidal stresses within the ice shell, when Jupiter's gravitational pull becomes strong enough to temporarily open fractures. In other words, these are not permanent conduits, but natural pressure valves that open only under the right conditions. The most widely proposed mechanism to explain this phenomenon is cryovolcanism, ice volcanism. On Europa, volcanoes do not erupt molten rock, but instead expel liquid water, ice, and salt, rich solutions from beneath the crust. When pressure builds within shallow water reservoirs or liquid pockets, trapped beneath the ice beyond what the overlying shell can withstand, material is forced upward through fractures and escapes into space. Under extremely low temperatures, the water rapidly changes phase, forming clouds of vapor and fine ice that can be observed from afar. Importantly, physical models indicate that the source of these plumes may be connected to the subsurface ocean, even if not all of them can be confirmed to originate directly from depths of tens of kilometers. Some scenarios suggest they may arise from shallow lakes trapped within the ice, sustained by the ocean below. Regardless of the specific pathway, the central point remains unchanged. Europa's ice shell is not an absolute barrier. Its plumes transform the ocean into a natural sampling system, lifting material close to space without any human intervention. Theoretical analyses suggest that material within the plumes may carry dissolved salts, ions such as sodium and magnesium, and potentially simple organic molecules. While such molecules are not evidence of life, they are crucial pieces for assessing the chemical richness of Europa's ocean. On Earth, environments rich in salts and chemical complexity are precisely where microbial life readily survives and adapts. However, Europa's plumes are not detected consistently, and confirming their presence remains a challenge. Some observations have failed to reproduce the phenomenon, leaving questions about their frequency and stability unresolved. For this reason, future missions such as Europa Clipper are designed with a clear focus, not to search directly for organisms, but to analyze the chemical composition of the plumes if they appear. Instruments on board will measure elemental ratios, identify the presence of organic compounds, and search for chemical imbalances that are difficult to explain through purely inorganic processes. This is how science approaches the question of life, with caution yet depth, not by seeking direct answers, but by seeking signs that an answer may exist. Life on Europa, if it exists at all, would likely exist at the lowest boundary of biology, where survival is not about growth or increasing complexity, but simply about maintaining itself against a cold and hostile universe. The first condition shaping every possible scenario is the complete absence of light. An ice shell tens of kilometers thick completely blocks sunlight, rendering all biological mechanisms based on photosynthesis impossible. This eliminates nearly the entire biosphere familiar to humans. Yet Earth's own history shows that light has not always been the foundation of life. For hundreds of millions of years, life on Earth existed without oxygen, without photosynthesis, and without a stable surface. In that sense, Europa is not an anomaly, but a reflection of Earth's deep past. The most plausible scenario is life in the form of single-celled microorganisms, similar to bacteria or archaea. These organisms would not rely on light, but on chemical energy. On Earth, chemosynthetic ecosystems around hydrothermal vents on the ocean floor provide the clearest example. There, microorganisms use redox reactions involving hydrogen, methane, ammonia, or sulfides to generate energy, build cellular structures, and reproduce. This is not speculation, but biology that has been observed, measured, and studied for decades. From a chemical standpoint, Europa does not lack the minimal requirements for this type of biology. Spectral analyses and geochemical models suggest that Europa's ocean may contain dissolved salts, metal ions, and simple compounds capable of participating in energy-producing reactions. More importantly, Europa is believed to possess all 6 core elements of biology: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. On Earth, every known form of life is built upon this framework. Even on our own planet, biology has demonstrated remarkable flexibility. There are microorganisms that live at temperatures exceeding 100 degrees Celsius, withstand pressures of thousands of bars, or survive in radiation environments intolerable to complex organisms. For this reason, it cannot be ruled out that Europan life, even if carbon-based, might use alternative forms of genetic mechanisms. DNA is an extremely effective solution, but it is not necessarily the only one nature could produce. Science does not claim that life on Europa would be DNA-free, but there is also no scientific reason to assume it must mirror Earth biology exactly. The ocean environment of Europa, if stable for billions of years, could allow life to persist for vast spans of time while evolving very slowly. Chemical energy, while sufficient to sustain biology, is typically far lower than the energy provided by sunlight. This limits metabolic rates and reduces evolutionary pressure toward complexity. In such a case, life might reach a long-term equilibrium, where the goal is not expansion or diversification, but survival within strict energy limits. If life on Europa were limited to single-celled microorganisms and never evolved into more complex forms, would such a discovery be enough to change humanity's perspective? Scientifically, the answer is yes. The existence of even one form of life not originating from Earth would be sufficient to demonstrate that life is not a singular anomaly, but a repeatable outcome of physics and chemistry under the right conditions. If life can exist in the darkness beneath Europa's ice, then many other worlds from Enceladus and Ganymede to icy moons orbiting distant planets become serious candidates as well. In that scenario, the universe is not an empty place with a single oasis, but a network of hidden oceans, where life may quietly exist beyond our sight. Europa orbits Jupiter at an average distance of more than 5 astronomical units, where the intensity of sunlight is only about 3–4% of what Earth receives. The ice shell, 15 to 25 kilometers thick above the ocean, forms an almost absolute barrier to external heat radiation. No light penetrates downward. There is no day-night cycle, and none of the familiar heating mechanisms that sustain life on Earth are present. So what has kept a global ocean in a liquid state for billions of years, deep within the cold of space? Its orbit is slightly eccentric, and more importantly, that eccentricity is not erased over time. The reason lies in Europa's gravitational lock within an orbital resonance with 2 other large moons of Jupiter, Io and Ganymede. For every 2 orbits Europa completes around Jupiter, Io completes 4, and Ganymede completes 1. This arrangement creates a stable gravitational rhythm that constantly pulls Europa away from a perfectly circular orbit. As a result, Europa is continuously flexed and stretched as it moves closer to and farther from Jupiter during each orbital cycle, which lasts about 3.55 days. The deformation itself is not dramatic to the eye, only on the order of a few tens of meters, but it occurs relentlessly over billions of years. In planetary physics, such repeated deformation is an ideal recipe for generating heat. Jupiter's immense gravitational energy does not vanish. It is converted into internal friction within Europa, warming the ice shell, the ocean, and especially the deeper rocky layers. This process is known as tidal heating. Modern thermal models estimate that tidal heating within Europa provides a powerful source of energy and, crucially, one that is stable over geological timescales. It is this stability that allows Europa's ocean not merely to exist temporarily, but to remain liquid for billions of years. A time span long enough for complex chemical processes to unfold. Heat does more than simply keep things warm. When generated from below, it drives thermal convection within the ocean. Warmer, less dense water rises, while colder, denser water sinks, establishing slow but continuous circulation. This turns Europa's ocean into a dynamic system where material is mixed, energy is distributed, and chemical reactions have repeated opportunities to occur. In the science of life, such circulation is essential. A completely stagnant environment eventually reaches chemical equilibrium and becomes dead. A convective environment, by contrast, maintains imbalance, and it is precisely this imbalance that underlies all biological processes. Even more importantly, structural models of Europa suggest that the ocean may be in direct contact with the underlying silicate rock layer. On Earth, the locations where primitive life is thought to have emerged earliest were not at the surface, but on the ocean floor, where hot water reacts with rock to produce energy-rich compounds. As water percolates through fractures in heated rock, geochemical reactions can release molecular hydrogen, methane, and other reducing compounds, ideal fuel for chemosynthetic systems. From this perspective, the hypothesis of hydrothermal vents on Europa's ocean floor becomes not only plausible, but difficult to ignore. On Earth, Hydrothermal systems, such as black smokers and white smokers, sustain ecosystems entirely independent of sunlight. Europa, judged by physical and chemical criteria, shares many of the same prerequisites: liquid water, a rocky seafloor, a stable heat source, and sufficient time. This does not confirm the existence of life, but it dismantles a critical psychological barrier: the assumption that life requires light. What life truly requires is usable energy and an environment where chemistry can persist over long periods. At a deeper level, tidal heating also affects the ice shell above the ocean. Upward heat transfer reduces the viscosity of ice in certain regions, allowing the shell to deform, fracture, and reorganize. This not only explains Europa's young and dynamic surface, but also suggests that the ocean beneath is not completely isolated. Europa does not promise life forms appearing clearly in front of a camera lens. The Europa Clipper mission is designed to carry out a cautious yet decisive task: to verify whether the intersection of liquid water, tidal energy, and essential chemical components truly exists beneath the thick ice shell. If these three elements converge, Europa will no longer be a vague hypothesis on an astronomical map. At that point, even a single biosignature, even an indirect one, would be enough to redefine humanity's place in the universe. Earth would no longer stand as a lonely exception, but as one among many worlds that harbor subsurface oceans. Europa would become compelling evidence that life does not necessarily require sunlight. It can quietly emerge and persist in cold darkness, hundreds of millions of kilometers away from its parent star. And if life truly exists beneath Europa's icy crust, a larger question will confront all of humanity. How many other invisible oceans are quietly drifting through the brilliant expanse of space, waiting for the day we become wise enough to see them?
While Earth is defined by its rocky mantle and iron core, the much smaller Europa is dominated by an ice.
Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.